Thanks. So now we have Louisa Fay, who is a PhD student at the University Hospital of Tübingen, and she will be presenting her FAIMI paper that won the best oral presentation at our MICCAI workshop. So Louisa, go ahead.
Okay, no, I think you can hear me now.
Yep.
Yeah, perfect. So thank you for the introduction, Emma. I'm happy to present our work today, which I present in South Korea as well, which was titled MIMM-X Disentangling Spurious Correlations for Medical Image Analysis. And so in this work, we aim to investigate how to avoid shortcut learning by disentangling spurious correlation to enable predictions based on causal features in medical image analysis. So to say it in other words, we basically try to enable predictions based on the right reason so that we can take predictions that are robust across different domains. So this work is motivated by the problem that conventional deep learning methods are only able to detect patterns in correlation training data, but they are most often incapable in identifying their real causal meaning. And particularly in medical imaging, many factors influence database cohort and thereby can create a spurious correlation. So to give an example, if we have two hospitals and both hospitals acquire brain MRI, but the first hospital, Clinic A, acquires mainly healthy subjects, while the second hospital mainly acquires subjects with Alzheimer's disease. Since we have two different hospitals, we use different scanners, which means the acquisition look different and they can create a bias in the data set. Now, if we merge this cohort to train a deep learning model to predict Alzheimer's disease from those brain MRI, the model will most likely learn the correlation, which is easier between the clinic and the disease, instead of learning the more complex causal relationships between anatomical features in the brain and the Alzheimer's disease. And this is obviously a problem because even if we take the correct predictions in the same domain, this would still mean that the predictions are not taken for the right reasons. And if we have a new scanner, we most likely would fail with our predictions because the spurious correlation doesn't hold anywhere. However, this spurious correlation does only exist if we merge cohorts. Even if in one data space, we can have the spurious correlation, if there's a common cause which creates a spurious correlation between a spuriously correlated factor, which could be the scanner as before, and another disease, for example. So we don't want to do that because we want our model to predict from an input image the ground truth label without being influenced by any other factor. Because if this correlation is spurious and we rely on the spurious correlation, this could mean that the prediction might be biased, or even we could perform a wrong diagnosis. So the idea of our work was that we create a model which is able to interrupt the shortcut between the spurious correlated factor and the ground truth label by minimizing the mutual information. So that in the end, our model is actually able to take predictions only based on causal features. So this was the first basic setup. But in real world scenarios, we might not only have a single spurious correlation, but rather multiple spurious correlations. And that was the idea, what we wanted to challenge in this work, or what we wanted to address in this work. And therefore, we created this model, which we call the mutual information model extended, which is able to address multiple spurious correlations. And this model, MIMM-X, operates on a feature encoder. And this feature encoder takes input image and encodes into a feature vector. We take in the end this feature vector and split it in n+1 parts. The aim is, by splitting this, that we can take one feature vector part, which is able to predict the primary task. So in the example before, that would be the Alzheimer's disease. With the n other parts, we aim to predict the spurious correlated factors. So if we think of the example before again, that would be the scanner or the acquisition side. And then we also have additionally this confounding attention rater, which gives different weights or learns different weights for the different spurious correlations. But the most important part, as mentioned before, we want that our model has learns causal features to take the predictions and has independent features, so that we don't share any information between the spurious correlated factors and the actual primary task. And therefore, we additionally add this MIMM module to our framework. And this module takes the primary feature vector part and the stacked sub feature vectors and estimates with this mutual information estimator the mutual information. The idea behind this is that we take this mutual information in the end as a penalty term in our overall loss function, so that we enforce feature independence during training. So the idea is that in the end, these two feature vectors are independent, because if they don't share any mutual information anymore, so if the mutual information is 0, both feature vectors should be independent. And the other two tasks, so like the primary task and the spurious correlated task, which you also observe, they are if we use classification, we just use cross entropy loss. But additionally, during training, we use this dynamic loss scaling, where we try to enforce more focus on the primary task, because this is what we actually want to observe. And about the training of this model. So we trained this model in an alternated fashion. This means we iterate through the batch, or like we have like kind of batch-wise training. So like we train the feature encoder for a single batch, and then we update the MIMM module for multiple batches. The reason for that is that every time we update a feature encoder, the distribution here changes, and this means the mutual information estimator would see a new distribution. So we have to adapt the model first before we can update the feature encoder again. And this update is a hyperparameter, which in the experiment I'm going to show you here is set to 5, but this is like a hyperparameter which has to be optimized during training. And in the scope of this work and also in the paper, we performed a lot of different experiments, but for the sake of time, I'm just going to present one experiment in this presentation. And in this presentation, we took brain MRIs from the UK Biobank and the German national cohort. And the idea was that the primary task to predict is the age group. So is the subject younger than 51 years old, or is it older than 57 years? And then we induce spurious correlations over the sex of subjects. So do we have a female or male brain? And the data set is from the UNACO or the UK Biobank. Now, for the training setup, we really want to make sure that there is a spurious correlation. So we induce this spurious correlation. And this means during training, we had like for the age group, like for the younger group and the older group, both the classes are balanced, but the younger group mainly consists of female subjects, while the older group mainly consists of old subjects. And it was likewise for the data set. And we have the same distribution during training and for this external validation set, which means they both share the same spurious correlation. But now we wanted to test how the model performs if the spurious correlation doesn't hold anymore, and if the model is able to successfully avoid the shortcut learning over the spurious correlation. So therefore, we inverted this distribution, which now means the younger subject consists mainly of male subjects, and the older group mainly consists of female subjects. And likewise, again, we also swapped that for the data set. So now we have a data set which also has has a changed spurious correlation compared to the training. And then additionally, we have a balanced data set where all classes are balanced. Now we also compared this model to different models in the paper. In this work, in this presentation, I'm only showing the comparison to the baseline model, which is literally the same model, but without the mutual information estimation. So we don't enforce during the training the independence. And with this, we can already go to the results of our paper. And what we can see here, what I want to highlight first are the spurious correlated tasks. So what we can see, like for both models across all the data sets, the accuracies are quite high. And this is kind of what we expected, because we expected that predicting from the brain MRI, the data set, and also the sex of the subject, or we know from previous work, that it is quite easy to predict. However, if we now have a look on the primary task, we see that for the baseline, between the validation set and the inverted test set, the accuracy drops tremendously. And this is a clear indication that since the spurious correlation doesn't hold anymore, the model was not able to learn the causal features, or like the features which are actually related to the age group, but rather it relied its predictions in the validation on the spurious correlation before. For our model of our framework, this didn't happen, because we have like quite robust or like quite stable accuracies across all data sets. And this tells us that we were able to avoid the shortcut learning and could actually take the predictions based on the age-related features. to visualize that, and I just want to show you this qualitative example. So if we take a sample from the validation set, which wasn't seen during training, but is like kind of in domain, so from the major class during training, which was a female sample from the NACO data set of the young group, both models predicted correctly. Likewise, if we have a male sample from the UK Biobank from the older group, again, both models are correctly. However, if we take a sample from the minor represented group during training, which was now an older sample from which was female from the NACO, the baseline fails to predict it correctly. And again, same for the male UK Biobank sample from the younger group. Okay, now with this experiment, we could already show, okay, we could avoid the shortcut learning, but we also want to make sure, can we actually, or were we actually able to separate our features? So do we still share information, or are we actually free from information? And therefore, to recap how the model looks like, I just have it here on the right corner. So what we did in the second experiment was we took the upper feature vector part, so the feature vector part which was used for the prediction or trained to the predictor primary task, and aimed to predict the spurious correlated task. And then also we took the FZ vector, so the spurious correlated subfeature vectors, and aimed to predict the primary task. So ideally, the accuracy would be close to 50%, because this would mean we don't share any information anymore. This feature vector that cannot predict the other task anymore. And so what we could see here, if we take the feature vector for the age group and aim to and try to predict the sex of the subject or the data set, we can see for the baseline, we are still far away from 50%, because we still achieve around 70% for both tasks, and we're still able to predict from the subfeature vector the opposed task. However, for our model, we were close to 50%, which tells us we don't have any information in this feature subvector anymore. If we took the feature subvector of the spurious correlated task and aim to predict Y, we are close to 50% for both models. This was also kind of expected, because we didn't expect that the FZ vector learns more complex features. So like that the spurious, or like that the shortcut was only over like the spurious correlated task, and that we do not have any information about the primary task in this feature subvector of the spurious correlated task. We also visualize this and with this t-SNE plot, and what we can see here is each point in this t-SNE plot represents the feature vector Fy, so the age group feature vector, but colored by its spurious correlated class. And the idea is that we don't have any information anymore, as said before, but for the baseline, we can still draw some nonlinear decision boundary for both spurious correlated tasks. However, for our model, we were able to remove this information because we're not able to see any clusters of this spurious correlated task anymore. And so we could be sure that we don't share any information in the feature subvector of the primary task anymore. And with this, we can conclude that we developed a framework which allows to learn causal relationships and thereby mitigate multiple spurious correlation and avoid shortcut learning. So we created a predictor which is robust to distribution shifts and able to predict the correct results even out of domain data and on underrepresented groups. However, right now we are using a priori known spurious correlation. So in future work, we aim to extend this by discovering unknown spurious correlation in the data, and also perform the experiments with more spurious correlations, and also perform or extend the evaluation on more sensitive variables in underrepresented groups. And with this, thanks for your attention, and also thank you for my group for collaborating on this work.
Perfect. Thank you, Louisa, and good to see you after MICCAI. We do have time for a question, I think, and just in time there is a question that popped in. It says, how does MIMM-X perform compared to more simple solutions like resampling the data to equalize distributions of disease prevalence or patient characteristics, kind of like what epidemiologists do to match control and disease groups?
Yeah, so we also performed this idea of rebalancing as a comparison method in our model, in our paper. And we have to say, like, actually, compared to other methods which were published previously about spurious correlation, rebalancing is one of the strongest comparison methods. So this means, like, if we just resample during training, or like in our training data set, if we resample the minority or the minor represented class, so we don't have the spurious correlation anymore, the model is quite, like, rebalancing performs quite well, especially if the tasks are of equal difficulty. So if now in this example I showed you, we had like the age group, which was much harder than predicting the sex of the subject. However, if we have like spurious correlations of equal difficulty, then it's sometimes difficult then the rebalancing performs also quite well, because the task is just of equal difficulty. Like the features are like complex, or the features of different tasks have the same complexity, and so it's easier. It's easier if you rebalance the data to actually separate the features. I hope this was understandable.
Yes, I think I got it. So hopefully I think if they don't, then they can maybe just type again and we can help them as we go. But thank you so much for your time. We appreciate it.
Thank you.
I guess I'll hand over back to, I think it was Gule.